Intermolecular force, basically, if you break down the word, inter means between, and molecule means molecule, covalently bonded substance. Now, intermolecular force just means the forces between two different substances. Electronegativity is 3.4. The electronegativity for hydrogen is 2.2. And I got that information by looking at table S on the reference table. So what's really happening is the oxygen is hogging the electrons. So in other words, most of this is going to be negatively charged because this 3.4 says that the oxygen is pulling the electrons away from each one of these hydrogens. So this is going to be negative, and each one of these hydrogens is going to be slightly positive. Now, I have this H2O right here, and I have another H2O. Because of this difference in charges, these water molecules will never come into contact like this. In fact, they'll orient themselves because water is liquid, or at room temperature it is a liquid, but when the water is in liquid phase, these are going to be attracted because this red is negative and the yellow is positive. So we have two here. Now when we add another one into the mix, it's going to orient itself three-dimensionally, but it's going to be a whole network of water molecules just kind of moving along like this. But the yellows and the reds are going to be touching, not the reds and the reds or the yellows and the yellows. And if they do happen to touch, it's going to switch itself and orient itself around. You can't really see that, but it'll be in one giant network. Now this intermolecular force, when we're talking about hydrogen with the water, this is called hydrogen bonding, and it is considered a weak intermolecular force. A weak one because this can easily be broken, and you've seen this happening before every time that you have water dripping out of a faucet. When the water drips, it has a long drip because the water's polar. It sticks to itself. However, it doesn't take much to break that apart. In fact, you can do it with your hand. Ammonia, or NH3, this, because the nitrogen is more electronegative, the nitrogen is going to have a slight negative charge, and each one of these hydrogens is going to have a slight positive charge. So if I were to put a water next to this, the yellows are positive, the yellow would hang out next to the nitrogen. The red, oxygen, would hang out next to the hydrogen. So if I had this drawn out, I will have it looking like this. And if I had another one over here, it would orient itself like this. So basically you're going to have areas that are positive, sort of attracted to areas that are negative. And that's an example of an intermolecular force. This is a particle diagram of water. So each one of these, through hydrogen bonding, is going to be attracted to the one next to it. So it takes a lot of energy to get it to go from the liquid phase into the gas phase. The hydrogen bonding is causing the boiling point of water to be higher than other covalently bonded compounds. For example, this is water, and this represents carbon dioxide. One carbon and two oxygens. Carbon dioxide does not have a high intermolecular force because it is a nonpolar molecule. So nonpolar molecule equals low intermolecular force. Polar molecules equals high intermolecular force. When you have an ionic compound, like for example sodium chloride, you have a positive sodium ion, a negative chlorine ion. This is the ratio. For every sodium, you have one chlorine. However, you've never seen just one sodium and one chlorine ion together. So what happens is it becomes a giant network. So you have another Na plus here, another Cl minus there. You have a Cl minus here, and Na plus here. I think you're getting the picture. Also, it's coming in three dimensions, so this is also coming out at us. So right next to this one would be a sodium, you got a chlorine, you got a sodium, you got a chlorine, and so on. Now each one of these chlorides is held on this side by a sodium, on this side by a sodium, up here by a sodium, down there by a sodium, in front of me by a sodium, and behind by a sodium. So that's held very, very, very strongly. This means that ionic compounds have incredibly high boiling points. And you will notice this because if you ever try to put salt in a pot, you boil salt water, the water will boil away before the salt does. And in fact, we don't have the capabilities in our houses to melt sodium chloride. The melting point is incredibly too high. So we have metallic bonds. This represents a lithium, another lithium, another lithium, and another lithium. Because these electrons are bouncing from atom to atom, this is actually held in a very strong network as well. So in terms of boiling point, metals have a very, very high boiling point, and you can find this out by looking in table S. All right, to summarize, now in terms of intermolecular force, we have metals have the highest boiling point. Then we have ionic compounds. Then we have polar covalent. And finally, the lowest boiling point will be the nonpolar covalent. An example of each one: lithium solid, sodium chloride, polar covalent would be H2O or NH3, and finally nonpolar covalent, Cl2 or CO2, which are both nonpolar covalent compounds. Thank you.